Thank you very much. It's great to be here. I don't know about you, I had a big lunch, so I hope you're all able to stay awake. I'll try to be very lively and cover the material that I plan to share with you. I spoke yesterday, some of you already heard me talk. I'll try to bring some new ideas to this talk, which is focused on the state of the U.S. industry. And I think there's a common belief that the U.S. is so big and, we do it all and we've got everything. But in this case, that may not be true. And in fact, my organization, QED-C, is a global organization. And so a lot of the information that I collect is not just for the US, it's really global. And so I had some trouble really preparing this talk where I was asked to sort of focus on the US piece. So in order to do that, I organized it first, I call it the inputs to the system. Next is the outputs from the system. And then a little bit about QED-C, similar to the previous talk where we heard about KQIA at the end, and there's a lot of similarities, which is perhaps not surprising. So this is a picture. Now I just want to say QED-C was created by the US government, but I am not part of the US government. So I got some startup money to create QED-C from the government, but now we are increasingly supported by the members of the consortium who are from the private sector and not from the government. But I wanted to share with you this chart, which comes from the most recent US government report on the spending under the US National Quantum Initiative. And you can find this report on quantum.gov. It's a great place to go for information about the US National Quantum Initiative. And so this shows the amount of spending year over year, and it has these different, they sort of have a little shorthand at the bottom for the categories, what they call program component areas, PCAs, and they include quantum advancement, so that's sort of fundamental advances in quantum science, quantum computing, quantum networking, quantum sensing, and then some category called quantum technology. You can go to the report to read more detail about what's in each of these categories, but it just gives you a sense, first of all, that the funding went up for several years and it's been relatively flat for a few years. I don't know if you're reading the news. Someone here who asked a question, they're reading the news. In the US, there's a lot of discussion right now about how much the government should be spending on everything, including science. And so the funding for our science programs is in the process of being debated in our government. The president, the way our system works, the president proposes a budget each year, and then the Congress actually writes the check. And we're in that process now. The president's budget came out. The proposed numbers were quite low. And everybody's a little worried about that. But Congress will make the decision on how much money, so we'll wait and see what comes out. So we hope, despite the fact that some things are going up and down, quantum is still a priority. This government, the Trump administration, has made that very clear. And so we expect the quantum budgets to continue at least this level, and we'll see what happens. Maybe it will increase. Okay, so that's what the US government is spending. They also have a number of programs, and I apologize for the small font. This is a program that some of you may be participating in, and some of you have been following perhaps. This is out of our Defense Department DARPA program, Defense Advanced Research Projects Agency, DARPA. And they're doing a program called the Quantum Benchmark Initiative. And under this initiative, they have three phases of the program, and we're right now in phase 1. And they ask for companies to apply to participate in the program. And in phase 1 and in phase 2, most of what will be done is evaluation by the DARPA team. They've pulled together a lot of technical experts, and all of the companies that are participating, that were selected to be part of this program, are getting a lot of evaluation from the DARPA team on their plan and their R&D plan and their business plan, and they are really trying to make sure that they've thought very carefully about what's needed to get their technology to what they call a utility scale quantum computer. So these are all the companies, and I actually made in bold the ones that are not US headquartered. So this US government program is funding companies that are based outside the US. Some of them have also got US operations, but their headquarters outside the US. And you can see the big range, and it's all big guys like IBM and then some much smaller companies. So this is a very interesting program where we will see what comes out of it. When you get to stage 3 of this program, there's potential for up to a few $100 million US. So at the end, there could be quite a lot of funding available, but right now it's in this evaluation stage. Okay, so that's part of sort of the US ecosystem on the government side. Now, on the private side, this is a chart taken from a report that was recently put out by QED-C. So this year, in March, we released the first State of the Global Quantum Industry report. And this is something that we feel is important to baseline this year, the size of the quantum economy, if you will. And how do you go about measuring economy? Well, you measure things like the number of companies, the number of workers, the amount of revenue. And so our report gives estimates for all of those. But it's not for the US only, it's for regions worldwide. So North America is all together, US and Canada primarily. And we did some analysis of the investment on the private sector side. Now, it's very difficult, of course, really impossible, for me to know what the amount of investment is being made by a big deep tech company like Microsoft or Google or IBM. That's happening inside the company, and they do not disclose that. They don't break it out from the rest of the company. And so we didn't try to estimate how much those companies are spending. This is reporting, and this is our numbers, but you can also see this from organizations like McKinsey, about the venture capital investment trends. And there was a dip in 2023, not just in quantum investments, but in a lot of investments. And in 2024, the dollars have rebounded to be the highest of any year measured back for several years. But the number of deals is down, so the average amount per deal is up. There are more Series B and later round investments. So this is kind of a natural evolution that you would expect to see in the venture community as a technology continues to advance. On the right is shown, and this was some data that actually broke out the United States, so I thought I'll share it with you. And you see the United States has the most venture dollars, and it's not linear in a sense. So you can see here, there's a break in the axis. It goes from 250 million to 1.7 billion. So the US is getting the lion's share of the venture capital investment at this time. So that sort of gives you a sense of what's going on in the private sector investment, or at least in the VC world. So that sort of is the inputs, I called it. Now I will sort of talk a little bit about the outputs. And if you're not familiar with this Australia Science Policy Institute technology tracker, I commend it to you. It's an interactive application that you can go and play with. It's really interesting, and what they are doing with this tool is pulling together all the information about highly cited publications. So that's a sort of caveat, something to keep in mind when you look at the results of their analysis. It's based on not just on quantity of publications, but highly cited publications, so that's good. But publications are not, products, right? They're publications. So if you go in there, you can put in different technologies, and one of them is quantum. And they've done some analysis and reporting. So when you look at one of their reports, they have the top countries in quantum computing, post-quantum cryptography, quantum communications, and quantum sensors based on, I'm going to repeat it again, highly cited publications. And when you look at that, you see that the US and China are number 1 and number 2 in all of these areas. And you can see the other countries that rank also quite highly. And then they have this second column. It says technology monopoly risk, and most of them are low, in fact, because no one country has more than a certain lead, percentage-wise. The first one, they seem to call it medium, and I guess they think the US has a sufficiently large lead that there's some monopoly risk in that case. They also show the lead institution, and you can pull that out of this analysis of the publications, and it's quite interesting to see which institutions, university or company in some cases, which country they're in and so on, are the top ones. Okay, so that is sort of showing that the US is lead, but you can see Germany, UK, and many others are doing also very well. So with this analysis, initially they only looked back about 5 years of publications. Recently they extended it all the way back to 2003, so now there are 20 years at least of data, and they started looking at time blocks. So in these columns over here of the rankings, first column is between 2003 and 2007. The second column is 2011 to 2015, and the third one is most recent, 2019 to 2023. And so you can see when it comes to quantum computing, now this is just the quantum computing one, the US is the top in all of these time frames, and China number 2, there's some variation below. And what's also interesting, I thought, was the institution rankings back in the early days. You see organizations like NIST, the National Institute of Standards and Technology, some universities here. And then when you look in the most recent time frame, IBM at the top, Google is on the list, and some other universities, and there's some change of order. So you can sort of speculate what's happening over time here, again, based on publications. So another output of spending on research and development is intellectual property in the form of patents. And QED-C has done some analysis each year, I think for maybe the last 3 years, of patent trends. So our methodology was to use keywords. We have a patent attorney in our membership, and he has done a very careful job of creating keyword lists that are good at capturing the patents without getting too many false positives and without too many false negatives. And so he's using that same methodology each year, so there's some ability to compare how it's progressing. And he has keywords that capture the quantum computing patents and another set of keywords for quantum communications. And you can find this on our website under the blogs, I think, section. And so this is showing the quantum computing patents. There's a lot of data I didn't put in here that sort of shows who are the top patenters, and IBM and companies like that are very high. But what I wanted to do in this report is to talk about country level in innovation. So when you look at the offices that are getting the most patent applications in quantum computing, the US is number 1, China's number 2, Japan's number 3, and then it goes down from there. Now, I want to remind everyone that a patent application that's filed in the US Patent Office could be an invention from somewhere outside the US, where the patent protection is being sought in the US. So you have to take that into consideration here. We haven't sort of done the deep dive to look at the assignees and where these patents are coming from. Of course, there's a natural inclination that a company will file in their home country and then maybe as well in other countries. In the case of quantum communications, it's reversed. Number 1 in this case is China by quite a lot, and number 2 is the US. And then the rest somewhat similar. So this suggests, and I think there was a lot of early reporting that China was doing a lot of R&D in the communication space, and so it's not necessarily surprising that this is the trend that you see when you pull out these statistics. And I don't have the years, it's over about a, I think, 5-year period. Okay, So we did this global quantum industry, state of the quantum industry report at QED-C this year, and I just wanted to pull out a little bit of information about the numbers, and this is showing the distribution geographically of what we call pure play quantum companies. So we all recognize that there were pure play companies, and then there were companies for which quantum was only a part of their business, and that's certainly true for the big tech companies like IBM and Google, but also for companies that maybe are making lasers. They may sell those into the telecom industry as well as to the quantum industry, for instance. So there are many more partial play organizations. About 6,000 were found versus about 500 pure play quantum companies. And when you just look at the pure play companies by region, the European Central Asia, it's quite a large region, but that's got the largest number. North America is rather close, and then you can see the distribution in other parts of the world. It'll be very interesting. We're planning to do this year over year to watch how these numbers evolve over time. And another measure of the global economy, of course, is the number of jobs. Now, again, it's not always easy to evaluate the number of workers at a big company that's not a pure play company. So we did try to track openings, because we can see those in the job advertisements, and then the actual workers. So for each of these regions, you can see the openings number and then the number of workers being estimated. And it's just, again, a chance to sort of look at the distribution worldwide. And I think it's really an important takeaway from these numbers is that there isn't really a region that is remarkably far ahead of the rest of the world. I mean, there is, you could say, Africa doesn't have much activity. That's not terribly surprising. But among the more developed economies, there's a lot of activity going on, both in terms of numbers of companies and workers. So this issue of supply chains is one that is top of mind. It's important for companies because they want to have a secure, robust supply chain. And so, but it's hard right now because the technology is very custom in many cases, and there are sort of reliable relationships that are developed, and so a company often doesn't have a lot of alternate suppliers. And we did a survey at one time and said, how hard would it be for you to find a new supplier if your existing supplier went away for some reason? And there were sort of estimates of it might take 6 months or 9 months or more to reestablish the supply chain. And so supply chains are very global, and they're somewhat fragile in the sense that they're quite narrow, I guess. And I would say that the tier 2 and tier 3 suppliers are often in another country. And so where you may buy a component, a laser or a cryogenic system or something from a company in country X, their supply chain probably goes across more borders. And so this whole web of suppliers into the quantum systems is extremely global already. And that makes it hard when you're a government to try to kind of control and own the supply chain for more, economic or national security reasons. And so this is where we are right now. Governments are asking themselves, are we sufficiently reliant on our own? Do we control our future in a way in this? Because it's a critical technology. And it's not easy to establish, I think, an internal an indigenous supply chain for everything to be able to feel like you own and control the entire supply chain. And so this last bullet, I think, is, we hear it over and over, the markets are small. Why would a new manufacturer get into making parts when there are not very many customers? There's not enough to sort of justify doing the engineering and the R&D that's needed in order to enter a market where it's just, a small pie and you're going to get a small piece of a small pie. So we're in that chicken and egg kind of situation. So I just have a few minutes left. I'll tell you a little bit about QED-C, which is a global trusted community of quantum companies and stakeholders in the broad ecosystem. We have a mission to grow the quantum economy. I've told you a little bit about that economy. We just recently did a sort of strategic plan, and we are focusing on enabling and engaging our members. We are a member-based organization. The members have told us we want QED-C to be a voice, a trusted voice for this growing community, and they want us to be continuing to inform policy decision-making. The government role is really important right now. So we're organized around a number of activities, identifying use cases, which really means identifying markets for quantum technologies, and the sort of gaps that need to be filled in order to get to those use cases. Gaps in technologies, gaps in workforce, gaps in policies, gaps in standards and benchmarks. And then we want to get the word into the hands of people who can help fill the gaps. We don't have a big budget at QED-C to fill those gaps, so we have to get that information out to the people who want to make those investments, whether it's the public sector or the private sector. And finally, we act like any sort of industry association. We really connect people with each other to find customers and suppliers and so on. And this is a diagram that didn't come out 100%, but it's got the 70% of our members that are corporate. And the corporate members are mostly small, the mid-sized companies. You hear a lot about the big ones, IBM and Microsoft and so on. But most of our corporate members are small to mid-size or startups, and 1/3 is not US, 2/3 is US today. And these are the countries from which we accept members. So we have a white list, and it's sort of all of Europe and India, Asia, some countries in Asia, Australia, Japan, South Korea, Singapore, and then North America there. So we are increasingly global, and we look forward to continuing to welcome the broad community to help address all of these gaps that stand in the way to the global quantum economy continuing to grow. So in conclusion, the US quantum ecosystem is, I would say, robust. The US government is not inclined to pick winners, and so right now there's a competition. Photons, superconducting, trapped ions, neutral atoms, who knows? And the US government generally doesn't want to get in and sort of put their thumb on the scale. That said, I told you about that DARPA Quantum Benchmark Initiative for a reason, because it is a little bit, maybe at the end of the phase 3, going to have picked some winners. So let's keep an eye on that. It'll be very interesting. I think that a barrier that's not getting enough attention is not necessarily the problem of error correction. There's a lot of work going on error correction. But I think we need more explorers for algorithms. So I'm putting out a call for, that's something that can be done. You don't need to have a big facility to be exploring for algorithms. So I think every country is equipped to unleash their people, their smart folks, to help find algorithms and define applications and ultimately use cases. So I think QED-C looks forward to being part of this global community. We are building bridges, as was described in the previous talk, and we work with our counterparts like KQIA and others, as well as collaborating amongst our members to drive forward in the areas of technology, workforce, standards, and identifying the future economy for the quantum industry. So thank you very much.